Hello everyone and welcome back to NL582, Modeling and Control of Electric Machines and Drives. So in the last lecture we started, or just you actually was continuing talking about the construction and theory of operation of synchronous machine. And we have just talked about, after we have known that the machine rotor holds the field winding excited by DC voltage, producing north and south poles around the rotor circumference, and these poles are just having the same magnetic flux magnitude, and it does not change polarity all the time because we are talking about DC excited winding. Okay, and if you're talking about the generator mode, which is the mode we are more concerned with when we're talking about synchronous machines, so we are applying external force to rotate this rotor around its own axis like this in any way, just counterclockwise or clockwise direction, whatever it is. And the stator of the machine holds the armature winding, which is three-phase winding like we said before, and this just winding will be subjected to the magnetic field coming from the rotor. While rotating this field, this winding will experience a time varying magnetic field, and that is the conditions needed for Faraday's law for generation. It's just you have a piece of wire or a coil subjected to a time varying magnetic field. That's why we just have a magnetic field which is constant in magnitude and direction here, but while you're rotating it using an external force, the coils, which is stationary, and the stator will experience a change in this magnetic field in both magnitude and direction. Okay, because it is, if you were seeing at any coil of those, like the A coil here, for example, so the A coil here, while this rotor rotates like this, sometimes it will be just seeing the center of the North Pole. That means experiencing North Pole with a high magnitude. Sometimes this chart starts just rotating like this. It will be subjected to less and less magnetic field coming from North Pole until the South Pole actually comes up here, and now it's just seeing a South Pole, like we just said before when we was driving the shape actually of the magnetic field crossing this. Okay, so that's why these winding and the armature are now subjected to a time varying magnetic field coming from the rotor poles, and now an induced voltage, a sinusoidal induced voltage actually will be induced in these coils. Okay, but because you have three phases, that means three separate winding and the stator separated by 120 degrees, now you're actually having three-phase output voltage from the machine. Okay guys, like we said last time, it is also the three-phase winding also now carries current, and I will be just trying to write those down now. So if I need to summarize again the theory of operation of the synchronous machine, and like I said, we are more concerned with the generator mode for now. We'll be talking about the motor mode at the end. Okay, so what's happening in this, we apply DC voltage to the field winding. Okay, and this creates magnetic field with fixed magnitude, polarity, and position. Okay, we're talking about just a winding like this in the rotor. So you have, for example, two poles, so you have a North Pole and a South Pole. Okay, if you're talking just about like this, it's a winding connected to a DC source, so it's now just two poles like this, North and South Pole. Exactly two poles, just an example. You can have as many poles as the design requires. Okay, but for simplicity, now talking about just two poles, the North Pole and South Pole. Okay, they have fixed magnitude, so they have the same magnitude and the same polarity. The north still north and the south still south, and position, okay, because it's not rotating from its own. Yeah, that's why after that we apply external mechanical torque to force rotor to rotate around its axis. Okay, so right now these poles start rotating around its axis in any direction you want now. Okay, and what's happened to the stator? The stator, like we said, having three-phase windings. So that is phase A, and that is the coming back, phase A dash, and that is phase B, and that is the coming back, phase B dash, and that is phase C, and that is the coming back of it, phase, sorry, that's not phase C dash. Okay, so while now these poles are just rotating around the axis, okay, the fixed armature, and for you to remember, I'm talking about stator for synchronous machine, winding will be subjected to time varying magnetic field coming from the externally rotated rotor poles. Okay, so the rotor of the poles have fixed magnitude, fixed polarity, but you are forcing them to rotate. Okay, that's why a certain coil in the stator will sometimes see a north pole, sometimes seeing a south pole, sometimes it's subject to the center of the pole, so it's having the maximum magnetic field, and sometimes it's not subject to the center of the pole, so it's not the maximum. So it changes now. It looks like it's changing magnitude and polarity while it's not. So the poles are not changing actually, but because you are rotating them and the winding in the stator are stationary, not rotating anywhere, that means those coils will see this magnetic field as time varying. Okay, and that's why we're doing this. Yeah, so it's all the conditions you need to have induced voltage in this winding. So induced voltage will be obtained in armature three-phase winding. Okay, like we said, it is sinusoidally and balanced three-phase voltage. Yeah, because they are just three-phase winding, that means they are just the same, they are just all the same number of turns and number of other things, so they're the identical three-phase winding and separated in a space by 120 degrees each. Like we said before, if you have the axis of phase A and now you're just having the axis of phase B like that, so this angle will be 120 degrees. Okay, and it's also now the axis of phase C, so you'll find this also to be 120 degrees. So you have 120 degrees phase shift between each winding and the next winding. They are all identical physically, number of turns are the same, they are using the same size of wires, everything, so they're just three identical winding, but they are 120 degrees phase shift. That will just give you three sinusoidal voltages, where those three sinusoidal voltages are just balanced. Okay, guys? So you have balanced three-phase voltages. Let me just grab you again the photo for the three-phase voltage we are having here. Okay, sorry. So we are just grabbing the photo. Yeah. So you will have three-phase voltages coming just induced in the stator winding like this. Okay, just yeah, so it can be different in colors. So again, I will just take out the names for those, but you get the idea. So you have three phase voltages like this coming on the armature winding or the stator winding. Okay, and now that's a generator. Okay, if the generator terminals are connected to an external electric load, okay, so it's resistance, inductance, capacitance, whatever it is, R, L, and C, whatever it is, and now that's R, L, and C because that's an AC voltage, not like DC machine. If you remember, DC machine, or just when we use a load on the generator terminals, it was just resistive, because for DC power all the loads are just seen as resistive, if you remember from your circuit courses. But if you're talking about AC, it can, yeah, you can have any kind of loads and you can just feed power to any kind of loads, R, L, and C. So if the generator is connected to an external load, whatever this load is, now you have voltage applied to this load, so current will move through the armature winding go into the load. Yeah. Also, the current of the armature will be three-phase sinusoidal. Okay, you get the idea. You have three-phase AC voltage applied to three-phase load. You will have three-phase current, like we said before when we talked about the three-phase connection, three-phase circuits at the very start of the course. Okay, guys. So you're now having a current moving inside the machine. Okay, guys. The whole point is, like we said before in DC machine, because the all concepts you wanna know. Okay, because now you have current moving inside winding. Okay, this current moves in the winding. Okay, so a counter torque will be developed, okay, opposing the main external applied torque. Remember, just like we said before, I'm talking about a generator or DC generator. If you have the shaft like this and you have the external torque external just applied in this way, and this is forcing the rotor speed to go in the same direction, so just having a current moving in the winding will generate internal torque inside the generator that is just acting on the opposite direction. So that is the torque inside the machine, so call it torque of the machine. Okay, guys, and that is how you just go to a steady state speed, how it's balanced each other, and you have a balanced system. Okay, guys, so that is the idea we're talking about here. It's just for a generator you'll be having something like that. But here's the whole point. In DC machine, guys, this counter torque was causing the speed to drop down, if you remember, because that was a torque speed characteristic of such a machine. But if we're talking about a synchronous machine, a very different thing will be just happening here. Okay, that the speed of the rotor, okay, has to be constant all the time, because any change of it changes the output frequency of the machine. Remember, it's a synchronous machine. NS equals 120 F over P. So any change you have in the speed of the machine will directly impact the frequency, and we cannot let this happen. Okay, that's why we use a control system called the governor, and that's very famous thing used with all the generators of the public grid to restore the speed back to its rated value or design value if the load increases. Okay guys, so that's the very important thing to have in mind. So this kind of machine has something we call the governor. I'll go back again to talk about these control systems we having over the practical typical generator we have on the grid in coming lectures, but it's a very important thing to keep in mind for now as engineers. Okay, so the whole point is, yeah, for a typical machine, if you increase the load, the counter torque will be increasing, and that means the speed should be dropping a bit, but we cannot let the speed of a synchronous machine drop like we said before with DC machines. Okay, because DC machines, the speed can drop, but it doesn't have this big problems we're talking about here. But if you talk about synchronous machine, that is synchronous machine having three-phase output, and this is connected to a grid. Okay, the grid has maintained a fixed voltage and frequency all the time. We cannot permit any deviation in the voltage and frequency. Yeah, there is a very small minor deviation that can happen because nothing is ideally okay, but that is something concerned a lot with the stability of the grid you are connected to. For your power system courses, if you have power system courses, you will be talking much about this. So for the stability of the power system, we have to make sure that our generator all the time works at fixed frequency and fixed voltage output. Okay, and how we do this, we have just a glimpse of this today. If you have an increase in the load of the grid here, that will impact you on the machine by having more current going out. And the more current goes out, that means this torque goes high, the machine counter torque. And that means the speed will go down and the frequency will go down with it. And we cannot permit this to happen. And that's why we have what we call a governor. Sometimes we call it AGC, automatic generation control. So they have two names, governor or AGC, automatic generation control, to control this, to restore the speed back. Okay, how to restore the speed back? That's easy because talking about generator. Okay, so the generator, you are just connected it to a turbine, to a mechanical system out there. So you're basically getting more fuel to the turbine here. That means you are increasing the input mechanical power. We are talking about the generator, guys, yeah? So our input mechanical power to it. So that makes sense. If your load increases, that means you have to increase the output power, electric power of the generator, and that comes by increasing the input mechanical power. Okay, and that will push your speed up again to be again back to the rated value, and that keeps your frequency at its rated value. So NS equals 120 F over P. So number of poles, it just keeps constant because that's a design value for the machine. You're not playing with the number of poles, was already operating machines. Okay, so just using this relationship and the frequency of the grid, which is 60 hertz here in North America. So you can work out what is the speed you have to maintain all the time to keep the frequency working at 60 hertz. Okay, guys? Again, we'll be just going back to talk about this control stuff, but it was to be just mentioned here. Okay, we're already talking about this because again, it's not just physics and equations, but it's all about engineering aspects of all those machines, how they are just will work while connected to its typical operating conditions. Okay, guys? That is what we call here the theory of operation for the generator. We'll be talking about the motor mode by the end of our talk about synchronous machine, maybe 2 or 3 lectures ahead. And I'll come back and talk about the theory of operation of the synchronous motor when I'll be talking again. Okay, that's very similar actually, but I will be talking about them again when I talk about this. Okay, guys? Good. That takes us to the very following topic. If you remember how we just dealt with DC machines, so in DC machines we talked about the construction of the machine, then we talked about the theory of operation, how the machine works, and then jumping to the modeling, how to model the machine and use derived equations and circuits to predict the performance of this kind of a machine. We'll be doing the same with all kind of machines. So with synchronous machines, we started by talking about the construction of the machine, and then talked about the theory of operation, and now I'm talking about the modeling of synchronous machines. Again, we are more concerned about the generator mode, but actually just apply to both of them. Okay. So again, how we model this, we use what we call the per phase equivalent circuit. Okay. So in DC machine, we call it just equivalent circuit because DC machine doesn't have phases. It was just DC machine. It's one winding, yeah? So just one winding in the armature, one winding in the field. So it's just one winding. But here we're talking about synchronous machine, which is typically an AC machine. Okay. So AC machine, you have to determine if it is a single phase machine or a three-phase machine. As we talked about synchronous machine, it's typically a three-phase machine. That's why we are just using what we call a per phase equivalent circuit, because you should have a circuit for each phase, because in the armature you have three different phases. That means you have three separate winding. Okay, that means you should have a circuit for each one of them. But luckily, we have what we call balanced three-phase winding, okay, fed by balanced three-phase voltages. If you're talking about a motor or it is a generator, it will be generating three-phase voltages balanced. Okay, that means, like we said before, it is just for all the phases, the voltages and currents will have the same magnitude. Okay, yeah, they have 120 degrees phase shift, but we are more concerned about the magnitude, because if you work out the magnitude and angle for just one of them, you can work out all of them. Okay, so that's why we just use one equivalent circuit to represent one phase of the machine, and by calculating all the values, electric values we use for one phase, we can easily find the other phases just because they are balanced. Okay, guys? So again, that is the same like what we said before in DC machine. We now have E phase, the induced voltage on the armature. Now I'm just having the armature circuit, okay? And it will be just like this. Remember, DC machine, the armature winding has a resistance like this, but now because we're talking about AC quantities, we will be having what we call JXS. The winding now, the coil will have a resistance and a reactance, because now you have an AC voltage or an AC current moving through it, not like the DC machine or just DC quantities. So in DC quantities, okay, we are talking about, so XS equals 2 pi f, the frequency, multiplied by the inductance L of the coil. It's just a coil like you just have before in your circuit courses. Yeah, this frequency for DC, the frequency equals 0, and that means these X equals 0. Yeah, so yeah, in DC machines the coils has inductances, but the reactance is 0, because the reactance depends on the frequency, and because DC excited, you will not have reactance. Okay, guys? But now, because we are talking about AC voltages and AC current moving in this winding on the armature, the winding, each coil will be just have to be represented by a resistance and a reactance, like that. Okay, we call it XS because it is just what we call the synchronous reactance, because just used with synchronous machines. Yeah, so that is the winding, and that is the terminal voltage. Like we said, if we talk about a generator like which typically you are having here, you will have the current moving out of the machine like this. So if there is positive negative, also the terminal voltage will be positive negative like that. Again, because like we said before, the Lenz law just permits the voltage out of the machine, or the voltage induced inside the machine, will be just opposing each other. So if this voltage trying to apply a current like this voltage will be trying to apply a current in the counter direction. Okay, which one of them will just determine the direction of the current? It depends on the mode of operation. If we're talking about a generator, that means the induced voltage higher than the terminal voltage, and this will push the current out of the machine. If you're talking about a motor mode, that means the terminal voltage will be higher than the induced voltage, and this will push current inside the machine. So it just depends on whatever mode you're talking about. It is the same like what we said before in DC machines, guys. Okay, but the difference, it is just you are talking here about an AC machine rather than to be talking about a DC machine. Yeah, so we are more concerned about generator mode, like I said. So the current will be just moving out of the machine like here. Okay, guys, and here we are connecting the load. And now I am just connecting load like that, and now I'm calling it Z load. And why? Because we're talking about AC. That's why that is impedance, Z, because it can have resistances, inductances, capacitances, whatever you are talking about the load here. Okay, guys? It's not like back in DC machines, you just have a resistance back there, okay? Because again, it's DC quantities. Yeah? That is the armature. So that is the armature per phase equivalent circuit. Keep that in mind. That is to the armature, and the most importantly, that is a per phase circuit. So keep that in mind. When I'm saying that means this induced voltage and induced voltage per phase, and this resistance is the resistance of one phase, and this is the reactance of one phase, and that is the current of one phase. Everything here is just for one phase. That's very, very important to keep in mind, guys. Okay, that means if I just given you the value of the terminal voltage, but in line-to-line quantities, like it's typically given, okay, you cannot use it in this circuit directly because that is a per phase circuit. That means everything here is a phase quantities, not a line-to-line quantities, like we said before in three-phase circuits review. Okay, guys, that's why I'm emphasizing that, and I'm just stressing this very much because that is the source of most of the problems and the mistakes we're having while trying to solving these circuits, is you just all the time forget that everything here is just in phase quantities. Nothing here is line-to-line quantities or three-phase quantities. They are all phase, single-phase quantities. Okay, guys? For the field circuit, it should be just the same like the field circuit in B4. That is field resistance, and that is V field DC, and that is I field. Why? Because that is the field winding or the field circuit. Why? Because it's fed from a DC source. So it's just like the same like DC machine, okay, because it's fed from DC source, okay? So it's a DC source applied to a winding, so the winding will be represented with just the resistance, because again, like we said here, in DC the frequency is 0, so you just don't have a reactance for here. Okay, guys? So what is the difference between this and the equivalent circuit of a DC machine? Let me remind you by the equivalent circuit of a DC machine. It was just like this. That was the E armature, and that is the R armature, and here the terminal voltage. Okay, that was for the DC machine. So you have one big difference. It is just in here we have the synchronous reactance, like I said, because we have an AC quantities. Okay, the other difference, remember those two pieces here we just usually draw for the equivalent circuit of a DC machine. In DC machine, those represented the brushes. Why? Because the armature of a DC machine, that was the armature circuit of a DC machine, okay? That is was the armature circuit of DC machine, yeah? And if you remember, the armature of the DC machine was the rotor, not the stator. So the voltage of the armature and DC machine collected using brushes, because if you want to collect voltage from a rotating member, which is the rotor, you have to use the brushes. You do not have anything to do. Okay? For here in the equivalent circuit of the synchronous machine. The armature of the synchronous machine, on the other hand, is the stator, not the rotor. So for this, it is the stator, okay? And the stator does not need brushes to collect its voltage because it's stationary, yeah? The stator does not rotate, does not go anywhere. So we just directly have the connections of the winding to the terminal box and just use them directly. But if you want to access a rotating member, which is the armature of a DC machine, which is a rotor, you have to use brushes. So that's why we used to just draw two black pieces like those, because just to remind you all the time, that is the armature and that is the rotor for this kind of a machine, guys, okay? So I will just a quick comparison between the two circuits, just to trying to solid this concept, how actually to derive and find the equivalent circuit for different machines, okay guys? And that's how we use it like here. Okay, so that was the perfect circuit of the machine like this. And like we said, here it's now easy. You can just use this circuit to find out the IA, okay? And I'm reminding you that's a phase quantity. PH means phase quantity because that's a per phase equivalent circuit, okay? So the current of it will be just having a magnitude like this, okay? And or our RMS value and an angle, okay? So it will be just theta of phase A, because we have three phases, A, B, and C, yeah? So this can be calculated from the equivalent circuit, okay? This, you can use the equivalent circuit here with all the information provided for you to find this value, the current magnitude or RMS value, and the angle, okay guys? And you can use this directly to find the other two phases. So phase B, the current of phase B will be the same magnitude and the same RMS value for this one, because they are balanced, that means they have the same magnitude. But the angle will be theta A minus 2 pi over 3. That easy. So you're also using the value for theta A here, but just you have minus 2 pi over 3 with it. And phase C current will be having also the same magnitude and same RMS value, but it is theta A plus 2 pi over 3. So that's why I'm saying, because they are balanced three-phase winding, we can just solve for one phase circuit, and you can just find all the other quantities for the other two phases easily because they are balanced. Of course, if it is not balanced, you will need three different equivalent circuits for each phase, but it's not the typical case we are just dealing with in our studies and in our machines, okay? Okay guys, so using like we said before, you can just directly find the equations. So the armature voltage equation, you can find it directly from the circuit. So E all equals V terminal plus IA RA plus JXS IA. Okay, why I'm having these dashes here? Because all of these quantities are just phasor quantities. That means each one of them has magnitude and angle. Why? Because they are all AC quantities. Keep that in mind. It's a major difference here, guys, compared to DC machines. Okay, so with DC machines, we are not playing with this. With DC machines, they are all DC quantities. You just care about the magnitude of each thing. So you just have the value for the induced voltage and the value for the current. They are all just one value because it's a DC quantities. But we are talking here about AC quantities. That means the voltages and the currents, every one of them will be just having both magnitude and angle. And that is why keep that in mind. That's very important to have. Okay, guys? Fine. And just to keep you informed, again, the terminal voltage here, V terminal, okay? And I'm going to have those two marks, that means the magnitude. And if you want just the magnitude, so you get rid of the upper dash here and just say V terminal, that means you are meaning the magnitude of this thing. For this equivalent circuit, that will be a phase quantity, like I said, because everything in just equivalent circuit is per phase. Okay? Usually it is given in line-to-line form in each information, because that's the typical way we deal in the public grid. Okay? So usually the armature three-phase winding are internally connected in Y or delta. Okay, so usually we don't have all the terminals of all the phases out, like 2 terminals of each winding, and now we have 6 terminals. Most of the cases the machine has a typical connection. Okay, so if there's a Y or delta, and you just have the terminals for the Y or the terminals for the delta outside for connection. Okay guys, so it depends on the connection. If it is a Y connection, that means the V terminal per phase will equal V terminal line to line, which is mostly given, divided by square root of 3, while the I armature phase will equal directly the I armature line to line, or the I of phase A per phase equals I the line to line, because that is how the connection Y works. Refer back to the second lecture if you just forgot this. Okay, for delta connection you have the other way, because now you have the phase voltage equals directly the line to line voltage. Okay, while the current, okay, of the phase will be just different from the current on the line. So the IA line to line divided by square root of 3. Okay guys, so that is the idea we're talking about here. So it depends on the connection. That's why I'm saying make sure you're dealing with phase quantities. So while we're dealing with this circuit, try to solve it, find quantities from it. Each thing inside this is basically per phase quantities. Okay, but if you want to calculate the line to line quantities, or it is given the line to line quantities, make sure you make the correct conversions, because before trying to go around and find anything else. Okay, that is very, very important to keep that in mind. I'm saying that, I'm stressing this much and much and much, because really it is just a source of big headache. Yeah, all the time the mistakes are just coming from this thing. Okay guys, okay, make sure I'm talking here about just the magnitudes of everything here. So those, I'm not using the dash on top like this, because I'm not talking about the magnitude and angle, rather I'm just talking about the magnitude. Okay, okay, and because we are talking about an AC quantities, it is much helpful to keep in mind the different phasor diagrams represented here, because so I am talking about the phasor diagrams. The phasor diagram, something just helps you a lot when trying to just have in mind what means by different directions of these phasor quantities, because each quantity of those has a magnitude and angle. Okay, so if we have the terminal voltage like our reference, and that means it is having a 0 angle. Okay, so that is V terminal like this. Okay, so that means I'm using this terminal voltage here, this value of the terminal voltage like my reference. My reference means it have a 0 angle, and that everything else will be referred to this value of the angle. Okay guys, so from the circuit if you want to work out the induced voltage E using this equation here, you'll be needing to have the terminal voltage value, and you add it to IA multiplied by RA, and to add it to J, XSJ as the complex operator and all this. Yeah, so by this value JXSIA, and if you add all those three together, you will have the value for the induced voltage inside the machine. So that's how we will do this, but because you will have those all like phasors, so each one has a magnitude and angle, so actually how you add them graphically using the phasor diagram. Okay guys, so that the terminal voltage V, and you add it to IARA. So firstly, let's plot IA. I will plot IA like this because I will start about talking about lagging power factor. If you refer back also to your circuit courses, so the IA, the current, can lag the voltage. That means it have a negative angle compared to the angle of the voltage like this, so that is theta, the angle between the current and the terminal voltage. And it can be unity power factor, that means they have the same angle, or they can be leading power factor, that means it is have a positive angle compared to the voltage. So we'll just have the three different cases like this here. Okay, so it is a lagging power factor like this, means the current angle lags the voltage angle, so it is in the negative like this, it's going down like this. Okay, and you need IARA to add it to the terminal voltage. So I will have the same phasor of the current here, so it is have the same angle, so it is parallel to it like this, and this will be just IA multiplied by RA. Okay, so that is how we add those two phasors together, the V terminal, added to IARA. But because they have different angle like this, we will just add them graphically using the phasor diagram. Okay guys, and then we add IA plus IAXS, like using this equation. I've already just had it back here. So E equals V terminal plus IARA plus JXSIA. So we now having V terminal added to IARA. Now we have to add JXSIA. The J operator means you have an angle of 90 degrees, and that is how we just plot it like this. We have this perpendicular to us, the 90 degrees, that is JIAXS. Okay, and the summation of those three phasors will give you the induced voltage of the machine like this, that is E. Okay, as a phasor. So E will have an angle between it and the terminal voltage, we call it delta. Okay, so for here, and that is a lagging power factor, don't forget this. So V terminal as a magnitude will have an RMS value V and angle 0, because we use it as a reference here, that is 0. That's a horizontal, like here, horizontal phasors, that means its angle is 0. Okay, and the IA here as a phasor will also have an RMS value or magnitude and an angle theta. Okay, the theta here is negative because it is lagging power factor. Okay guys, and E will also have an RMS value and angle, and the angle here is delta. Okay, because if you just have the voltage angle to be 0, that means you're using it as a reference, so you can find the angles of the current to be just like this. It's minus theta because it's lagging power factor, and for E it's positive delta because this angle is just up like this. Okay guys, so the delta, we call it the load angle. Sometimes you call it the power angle. Why? Because if the load goes up, and that means, by the way, the power goes up, this angle delta will also go up. So that's an indication of the load. So if the load value applied to the generator goes up, this delta will also go up. Okay guys, so this delta is the angle between the induced voltage and the terminal voltage. Yeah, and by the way, it is also have a physical meaning. Okay, how that? bear with me for a second. That's very important. Remember when we talked about the rotor here? So the rotor have a north pole and a south pole like that. And here the stator with its three-phase winding. A dash, B dash, and C dash. Yeah? Like I said by the end of the last lecture, and that's very important, if you don't remember, please review it. Though three-phase winding, because they are just connected to external load and a three-phase current will move through them. If you remember, if you have three-phase currents moving in three-phase winding, the poles, the magnetic poles, will be resulted from them because they are coils and having current moving through them, so they are also will be act like an electromagnet and have poles. Those poles, like a north pole, a south pole, a north pole, a south, a north, a south, they are rotating because, like I said in the last lecture, a three-phase winding fed from a three-phase supply. That means three-phase currents moving in the three-phase winding. Those poles will be rotating around the circumference of the stator by the synchronous speed, 120 F/P. Okay, guys? So the idea of this, that means you have a main magnetic field coming from the stator, these poles of the stator, the north and the south, okay? But actually, that will happen here is I will be having them differently. The south will be up. Sorry. And that is the main magnetic field that is coming from the rotor, the south and north of the rotor, okay? But those other north and souths that comes from the stator now are those induced poles, because the induced voltage comes in the stator and the current moving in the stator winding because it's connected to a load. So this current moving into the stator winding will produce also magnetic poles. And the way all the machine works, that the magnetic poles of the stator is just be coupled with the magnetic poles of the rotor. Each north pole of the stator will be coupled to a south pole in the rotor and vice versa. And because the rotor is rotating in some direction, and these poles of the stator is also moving in some direction, so they will be coupled together and rotating together at the same speed, which is the synchronous speed, ns, 120 F/P. Okay, guys? That's actually how the machines work. If the poles, the main poles coming from the rotor and the poles that be induced in the stator, each north pole in the stator will be coupled to the south pole, and the rotor will start rotating together at the same speed while they are coupled together. Okay, guys? That means if you want to just have it graphically plotted, so I will have the flux density of the rotor like a plot like this, that is B rotor, okay? And this is just rotating around with ns, 120 F/P, yeah? If you want to have to plot the flux of the stator, it should have the same angle like this. Why? Because like I said, they are just coupled together and they are rotating together by the same speed, ns. Okay, guys? So those phasors rotate around, but they have the same angle like that, because that's at the beginning. Okay? But if the load goes up, okay, like we said, if the load goes up, that means the counter torque of the machine, T counter, or like we call it the machine's torque, will go up. And that means the speed of the machine, the speed of the rotor speed will go down, but transient. That means it will go down for a fraction of a second. But our governor, our control system will restore it back to its value. Like we said before, we cannot let the rotor speed to go down. Otherwise, that means the frequency will go down, and we cannot let this happen. Okay, guys? But what happens in this fraction of a second when the rotor drops a bit before we just raise it back to its steady state value. Okay, this, if this happens, that means this rotor field will be just behind a bit, like this. Okay, and this is still the stator flux. Why? Because the rotor is the thing that slows down, because it's a mechanical brake acting on the rotor. It's not about the field of the stator. The field of the stator is just coming by electric current moving in the winding, so it doesn't have any means to slow down. Okay, so those guys will also keep again rotating at the same speed, but now you have an angle between them. This angle, guys, is the same angle, delta. Okay, so delta is the angle between the terminal voltage and the induced voltage, and it is also the angle between the rotor field and the stator field. And that's why I'm saying this is a translation for the load. With the increase in the load, that is directly translated to an increase in delta. Okay? That means you still have a north pole from the stator and a south pole from the rotor, that is the stator, sorry, and that is the rotor. And they're still coupled together by just magnetic attraction, a north pole attracted to a south pole, and they're still rotating together in some space. This was delta equals 0. But as delta have some value, that means the load goes up, you'll just have some deviation like that. They are just like this. The north of the stator like here, and the south like there. They are still attracted and still rotating together, but now you are having an angle between them. Okay then? Okay, guys? So they are still coupled together because they're still close to each other. So they're still coupled together and rotating together at the same speed, but now you will have a little bit of an angle like this. And this angle is delta. The problem is if you keep increasing the load, this angle delta will keep increasing until this bond breaks. So those poles, the pole of the stator and the pole of the rotor, are too far away, so they cannot be coupled together anymore because the angle between them keeps expanding because the load keeps expanding. And that we called the machine goes out of synchronism. Okay? And that happens if the load goes up too much, and this will result in delta goes up too much until there is no connection between the poles of the stator and the rotor, and the machine goes out of synchronism, and that means a failure of the machine. The machine has to be just tripped because it now means it's a very high load and the winding will start burning. Okay, guys? So that's the physical meaning of the angle delta, and that is how much this angle is very important. In your advanced power system courses, you will be studying how this angle has to be monitored all the time to keep the stability of the power system. They call it small signal stability. If you have the advanced power system course, or you will have it in later terms, you will be having much deal with this angle delta. Now you should understand the physical meaning of this angle delta. Okay? That is the angle between the terminal voltage and the induced voltage, and it's also the angle between the phasor of the rotor field and the stator field. And that means now you should be understanding why this matters and how this is translated inside the machine. More load means more delta, and that means more angle between the phasors of the rotor field and the stator field, and we do not like this because that means the machine is going to be out of synchronism. Okay, guys? So that was the lagging power factor. For unity power factor, okay, unity power factor means if there's the terminal voltage, the current will be having the same angle with the terminal voltage because that's unity power factor. And that means easily you can have IARA like that because in the same direction, and that is JIAXS because it's just perpendicular to it, and this will give you EA, or the induced voltage in the machine, like this, and that is angle delta. Okay guys, for leading for leading power factor, the phasor diagram will look like this, because like now you will have terminal voltage in this direction, still have zero angle, but now IA is leading, that means it's up here, and that is the angle theta. So IARA will be perpendicular to it because have the same direction, IARA, and now you on perpendicular to it here you'll have JIAXS, and by the end of this you can just have the summation of it to give you the induced voltage E, and that is now angle delta. So it depends on which power factor direction it is, lag, lead, or unity of the machine's current, to just know how to use the phasor diagram to find the induced voltage of the machine E. Okay guys, so that's it. Now you know how to model the machine using the equivalent circuit, and how to use the equivalent circuit to find the different values of the voltages and current inside the machine, and how to find the other phases quantities just by knowing the first phase of the machine, because it's balanced. And you know now how the load affects the machine internally, and how the angle delta is very vital for the operation of the synchronous machine. Okay, I think that's enough for today. Thanks so much for joining me guys, and I hope to see you next time.